Did you say we might print out the exam before?
Yeah, also, I can get it printed out tonight.
I had no urge. I stayed up really late studying and packing. I hate packing. And actually, it's surprisingly didn't take me that long to pack. I am such an overpacker though. Yep, every single one.
This morning, of course, the main printer keeps going down. And then I was like walking around the building and the people using the printers around the building ran every printer out of toner and no one said it.
That's probably our teacher. We had an immuno test today.
Wait, so the printer's not working?
Oh, you're still taking your test.
Yeah.
I was gonna say, if
Written out all the questions and all the work that it showed.
No,
Okay, I didn't.
no, if it's not working, I can't get a stack of them. You'll get an email telling you to print it out and bring it with you to the lab.
Okay. Okay, I was just wondering. I was just wondering.
No. Yeah, we're just doing the exam.
Oh, only exam tomorrow, no lab too?
Right.
Okay, thank you.
I tried.
Yeah, we'll just do the exam.
I tried. This next one.
It's so.
Okay, so while we were talking about, we're into the idea of work.
Bro.
So you remember, work is force transferring energy to a system.
Oh, yeah, going next week.
For example, you push something, you have to transfer a force to the object, and then the distance, so that force applied across the distance is going to be the work done. And so it comes out in units of energy. So, we started with a very basic example.
I think so.
So then to kind of review, it's like, we had an object that was here, okay? But it gets moved. Here. Across the displacement. And of course, generally, you can say you have a force applied at some angle. So then, of course, the part of the force that's actually going to move the object is the one that's going to be parallel to the direction of motion. So the part of the force that's actually going to move the object is going to be that component right there. So we talked about the most general definition of work is going to be your F dot delta R. So this is going to be a dot product of two vectors. So you're going to have, you'll have two basic definitions for this. Now, if you have two vectors with components, your work in this case, and this is called the scalar product. So you're not going to produce another vector. So you remember, if you have a vector with components, this one is going to be x component plus y component, y component. So that's one definition of the dot product. The other definition that's going to be more common for solving problems in this textbook is going to be so looking at that general example where you have a force pointed at some angle, that's where you can see this definition of the of work come into place. This definition of the dot product. So you're going to have the magnitude of the force vector, the magnitude of the displacement, and the cosine of theta between the two. So if you remember, say that's your force vector. That's your displacement vector. Your dot product will end up being you'll have the magnitude of one times the magnitude of the other times the cosine of the angle between the two vectors. So these are just two different definitions for the dot product. But like Yoda tells us, we'll get to a point where you'll see your second form of vector multiplication. The dot product is always going to be your scalar product. When we get to torque, you're going to experience what's called the vector product or the cross product. I'll show you the analytical version of that. I'll just never expect you to do it because I don't think anyone's taken like Math 400. You're going to have to like to do the analytical version of the cross product. You'd have to be able to do full on like matrix mathematics. I'll show you how it works. It's just not something you're going to have to reproduce. Okay. Now, another way you could look at this, let's say we have an object. Well, we know it's not a cat because cats are circles, but a couple things we do know. So the object's going to have a gravitational force. Let's say it's falling at along some path. And that way is your delta R. So it's falling along that direction. Okay. Now you notice you still have an angle theta between the force and the displacement. So then in this example, you could go ahead and finish off your triangle. Okay, and so what you're going to have down this side of the triangle, you're going to have a displacement vector of r cosine of theta. So when you're looking at this, remember in the first one you had the component of the force vector. This time you have a very similar thing of the component of the displacement vector, and you still so magnitude of one, magnitude of the other, cosine of theta between the two of them. Now, one of the ways to think about this is we're talking about what part of which vector is going to be involved in the movement. Now it's usually easiest just to look at which part of the force is going to be moving the object, and that's going to be the one we as you saw, it's going to be parallel to the displacement. So you can have a maximum amount of work done say this object was moved across some displacement by a force. Now this entire force is in the same direction as displacement. So this is going to be a pretty common equation that you'll find that can help solve problems. I just want to make sure you're able to tell me where it comes from. Because again, if we look at the work done, but then the question is, what is the angle theta? 0. And look at the direction the force is pointed and the direction of displacement. If they're both parallel and they're pointed in the same direction, the angle is 0. But for example, you'll see we can get negative work. So imagine that the block was moving that way, but I'm applying a force that way to slow it down. So just as an example, what if you were trying to slow it down? I had a force applied that way. What would the angle between F and delta R be? 180. So you just kind of look at which way the force is pointed. You can get an idea if it's going to be positive or negative. But with this here, you're going to get a maximum work done. What's the cosine of 0? 1. That becomes 1. You end up with F R. So your displacement. And of course, if you're only looking at a single dimension, you can say, well, this is the same thing as F delta X. Work in the Y direction, P force delta Y. Same, they're all the same, like same idea. Just remember your second part is going to be a force multiplied by a displacement. To kind of get an idea of what that might look like. That there. So of course, this time you see that you can just say your displacement is delta X. If that's your force, then when you do the work for this one, you're just going to have F delta X because, again, your force is pointing in the same way as delta X, so your theta is going to be 0. Let's see. Well, we'll get to some where, for example, the force of gravity is going to create negative work. This time you can say your object moved that way. So again, you see that the angle between the two is 0. There's one where you have F delta Y. Okay, so we talked about work can be positive, negative, or 0. So let's look at our common situation here. Now, let's say, for example, there's a force being applied. Look at those two velocities. You see your displacement. You see what's happening to the velocities. Do you think this would be a positive, negative, or 0 work done? Positive. Because which way, like, You might not know exactly which way the force is pointed, but generally, which way is it going to be pointed? Yeah, so it could be anything, it could be any force, like, it could be like that, it could be like that, it could be like that, like that. It's generally going to be pulling the object further to the right. Do something like that. And so you notice you see your theta there. Now, how much am I supposed to get on this slide? Okay, so you're going to notice that your work when you're looking at an angle of less than 90 degrees, you're going to have positive work. So this time we're going to be a little more abstract. This could be 90 degrees. Like here, you see that force vector would be technically going up into the first quadrant. You could also have it going down into the fourth quadrant, but still, it hasn't reached a full 90 degrees in whichever way it's rotating. So it's still going to be an overall positive work. Now, what if similar scenario? Our displacement's still in that direction. Watch what happens this time. What happened? Yeah, so the velocity is decreasing. So in general, which way is the force going to be pointed? The applied force is going to have to be going the other way in some general way to have a component that will slow this system down. So we could say it's something like, oh no, let's do this one. This be confusing. That's going to be an angle greater than 180, but it'll still be negative. I don't know, either make it like second or third quadrant. It's going to be the same principle. Okay, now, where do you think I'm going to measure theta from? With what? Yeah. So my theta is like that. So in this case, so this means work is going to be negative, and you have a theta greater than 90 degrees. So again, it doesn't matter which way you're rotating. You could go clockwise from the positive x-axis if you ended up in the third quadrant. Let's say maybe you went for 120 degrees. This one here, maybe you went for 140 degrees counterclockwise, and you're in the second quadrant. Either way, you're still going to have a force vector that's going to have a component that's pointing away from the displacement, in the opposite direction of the displacement. That's going to give you a negative work done. Now, here's a question. say I have this. What is the work done here? What is the angle between the force and the displacement? 90 degrees. Yes. Because if you didn't get that right off, go ahead and put the 90 in there. What's cosine of 90? That's 0. Work is 0. When you have a force that's perpendicular to your displacement, you have no work done.
Does work have units?
Yes, units of energy.
Oh, yeah.
Newtons times meters, Newton meters, which is what? Joules. So then here's a question. What if we think back to let's say we had no, I don't want A. A. Okay, so now let's say we have a circular motion, okay? So I have some particle going around the circle. I have the center of the circle. So now I have a tangential velocity going that way. So remember, that's my linear velocity. What way is the force pointed? In this case, yes, but more specifically, which direction? What if that object moving in the circle was to move a little bit? It still wouldn't be downward then. Which way would it be? We're all going to point which way?
Up.
Test.
Does it have anything to do with like the radio and like?
Uh-huh.
Yeah,
Like
it's all
that.
radio.
So like, it's like 90 and then there's the middle one, right?
So the force that keeps this object moving in a circle is what? Centripetal. Which way does it point?
Inwards.
Towards the, always towards the center of the circle.
That's what I do.
We just didn't know the right word.
You just say force radial, force centripetal, same thing. But I would still err on the side of centripetal, your sub C, because when we talk about centrifugal, I'm just going to call that one radial so we can separate centripetal from centrifugal, because they're both a radial force. And what do we remember? What do we remember about tangential velocity? So linear velocity and the centripetal force. What angle do they form with each other? 90 degrees. So that means when you have this object going in a circle, the work done by the centripetal force is 0. Looks like I put an extra slide in there, didn't I? Okay, so are we kind of clear on it's going to be a negative, positive, or 0 work? Great, then we're ready to start the relativistic calculations of negative, positive, and zero curvature to the universe.
Fantastic.
One of them means that the universe is a sphere. One of them means the universe is a donut. Guess which one I'm hoping for? One of them means the universe is flat and infinite. Those are fun calculations.
Why Earth is.
Well, Earth is not flat because there's a central point of mass, meaning there's a central point of gravity in every space-time geodesic in the region. When we warp into that center of gravity. Now, granted, each space-time geodesic will be a differential apart from each other space-time geodesic, and when you draw a surface across those, you get a what? Circle.
See?
You believe in dinosaurs?
I love how that veered off.
No, this is actually on topic.
You know what's funny is when I ask in class, you can't tell me what a tangent is, but yet you demonstrate one so amazingly.
Oh, yes. So yes, you do, right?
Yeah.
We have like a
The bird
bottle of
lizards.
I think it's
French
rage bait.
The bird lizards. I don't
Right?
know.
Yeah.
Nobody can agree. Are they birds? Are they lizards? No.
I think people who don't believe in dinosaurs.
Maybe.
No, those unicorns, they just didn't get on Noah's Ark.
Actually, if you look, there was technically a unicorn back, but it was more akin to a rhinoceros. And it wasn't magical.
We said in my theology class in high school, we were like, the unicorns were just thought they were better than everyone did get on Noah's Ark.
No, that's the problem. You talk about a unicorn and everyone's like, that's completely ridiculous. But tell me which one is more believable. A horse with a horn or a hybrid brontosaurus leopard moose camel with little nubs on its head.
So real.
Which one's more believable?
Say it like that.
Yeah, Austin, so say it like that. But unicorns just thought they were better than everything.
Yeah.
They exist, don't worry.
So let's say we have a bicyclist climbing a hill that's 2 kilometers long, makes an angle of 2.6 degrees with the horizontal. The total weight of the bike and the rider is 750 newtons. How much work is done on the bike and rider by gravity? See, now that's something you can do. Anytime someone asks me what I weigh, I always use newtons because I'm not about to tell them something they understand.
4 newtons.
God, I wish. Hello diet program. I'm smaller than a toddler.
Fire.
Toddlers are like 30 something. Actually, then that'd be more. Still, if you're 4 newtons, you're technically dead.
Shit.
Like there's nothing but dust.
And that's a bad thing. Then I'm gonna take my biochem exam later.
Nope, gotta take your biochem exam.
Then I
Once you take your biochem exam, then you have my permission to die.
Okay.
So you don't have to take the physics exam.
I could die before my physics exam.
He didn't think that through.
You don't care.
Well,
He's like, sure.
I don't think either way is gonna help y'all then.
He was like,
I don't understand why I have to take the biochem exam and then die. I mean, it's not gonna matter in the end.
Easy
I'm
hundred
dead.
for the class, right?
You want me to feel the pain?
Remember, pain is pleasure. That's why we take biochem exams.
That's so real.
Stunning prey, investigating prey.
Now, granted, that's a lot steeper than 2.6 degrees, but we'll get the point. We'll do that. Okay, so
Amazing job. Yeah, they kill it. Great company.
person on bicycle is a rectangle. Now, let's think about what we have going on here. Okay, well, you have an angle theta.
I went to I think I'm taking my senior.
It was sick. And I didn't know. Sitting there in practice like this.
I'm at 12.
So it was like,
So let's see.
I'm like, oh my God.
Give delta R.
Year and I was only at
And like,
12 credits. Physiology, physics two.
Yeah, next semester is all about the stuff that affects your world that you can't see it. So,
So it's pointless.
no, it's gonna be field mechanics, but
So it's just what keeps me on the world.
actually, yeah, gravity is a field.
Sometimes I wish the gravity would just stop working and I could float out of this thing.
So we have our gravitational force vector or a weight. Force. Velocity. Oh, let's see.
Semester.
that was his first year.
So we have a we have a setup that we've been used to. One of the things we're gonna have to think about with this is,
Yeah, they asked.
we're going to think about this entire track as a triangle. So, what do we know?
You're on your sheet. It's a really cool custom.
Delta R is 2 kilometers.
Maybe they were full.
No, it's human.
Theta is 2.6 degrees.
Did they release?
Why is the x component of the weight negative?
Gravity's down.
That's one reason, but look at the direction of the x component of weight and the direction of displacement. Yeah. So we're gonna get like a cosine of 180 degrees there.
It was actually quite nice. Like, very, very light.
So the one W is work and the other one is late.
Yep. So
Yeah. Pissed off.
let's think of this in 2 different ways, okay? We're gonna bring the negative sign in 2 different ways. All right. We can start out with the negative sign because we know that the x component of weight is pointing in the opposite direction of displacement. So we can say, what is the work done by gravity in this case? So you see the direction of velocity, you see the direction of displacement. The x component of your weight is the one that's going to be working against your displacement. So that's going to be the work done by gravity. So what you can say, okay, and you can know that they're pointed in opposite directions from each other. So, and they're parallel. Okay, so you're still going to get a maximum force because they're parallel. There's not some measurable angle between them. Okay, so you could say that this is naturally going to be a negative. Negative x delta r, or wx delta r. And so that would be a negative theta delta r. How do we deal with sine of theta? There's something else I'm trying to get for, so I want to do that. We know weight is mg. Where'd that come from?
I'm sorry, that's weird.
Height, yes. Where did h over delta r come from? Right, the sine of theta is going to be h over delta r. And yes, you could put theta in there and solve this problem, but I'm trying to build up to something that's coming a little bit, right? So then what you end up with is a negative in GH, okay? Now, the other way we could look at this.
Oh, no, intrigues with that. Really? Well, yeah, as far as.
Let's try and make that, try and differentiate.
My friend, dad,
Work,
he goes on like 2 cruises. He goes on
the
a
gravity, it's going to be your x component of your weight.
Dude, he goes on like
R,
7 cruises a year.
which will give you W cosine of theta. And this time, if we don't start out putting the negative in there, what is the theta between? So again, they're parallel, but they're anti-parallel, which means it's a theta of what? No,
Wait, they're
anti-parallel is an angle of what?
parallel, so 90 degrees?
No, that's perpendicular.
Okay,
Parallel is pointing the same way, anti-parallel is,
going the opposite.
that's an angle of
180
180.
degrees.
And then, of course, our WX is still going to be negative MGH over delta R. So either way, you're going to end up with your negative mass times gravity times the height at the end of the displacement. Personally, I prefer to do it the second way, where I just start with the dot product and I look at the angle between the two vectors instead of trying to think, well, that x component is pointing in the negative direction, and then just trying to deal with it that way. So then from here, you say, well, your h is going to be delta r sine of theta. Because again, you could have just left this in there and solved it. But again, we're trying to build up to something. When you put your negative, I know we're backtracking a little bit. It'll make sense in a few slides. 750 newtons, delta R. 2,000 meters. Sine. 2.6 degrees. And the work done by gravity. Negative 68,044 joules. Or negative 68,04 kilojoules. Eventually, the movie Back to the Future is going to make a lot more sense to you when we start talking about gigawatts, but you kind of get the idea of just like if you just start with the basic definition of your dot product and you look at the two vectors. So in this case, you're thinking about, well, I need to figure out what part of that gravitational force is working against the motion or working with the motion. And so you notice that it's that x component of the weight points in the opposite direction of the displacement and the velocity. So you know that that's going to be working against the motion of the object. And so, okay, well, since they're anti-parallel, they're going to have a 180-degree angle with each other. That's going to make it, so a cosine of 180 is a negative 1. And so we're going to end up with a negative work done. But we're going to have systems where we have to deal with total work.
Yeah, I was there. So this is even better.
And so on and so forth. We can have work done by a lot of different sources. Well, but what if we change this to total work we could have a vector sum of all the forces present. See where that resultant lies. This is one of the reasons we use indices, because if you didn't use the indice, you might think that you're doing a sum over all delta r's and cosine of thetas as well, but you're not. It's only the sum over all the forces present. You see, only the force has the indice on it with sub I. Okay. I think an example will work best here. Sled pulled on level ground at constant velocity with a child riding on it. The total mass of the child in the sled is 26 kilograms. The cord that's pulling the sled makes an angle of 30 degrees with the ground. So you have a kinetic friction force with a coefficient of 0.16. Find the tension in the cord. What is the work done on the sled by the person pulling it for 120 meter displacement? And what is the total work done on the sled? So to start understanding everything that's present, what's the first thing we need? You have a free body diagram. Sled in kid is rectangle. Sled is mostly rectangle. Kid is subsumed into sled, becomes part of rectangle. The force pulling it is causing the tension in that string or that cord. Force. Gravitational force. One more. Kinetic friction. Then, of course, your tension going to have components x and y with your angle theta. So we have positive x and positive y directions. And one thing that's important from this, well, we'll start with this. Now we're running out of time. I'm gonna start part A, and I want you to tell me why this is the case. Okay. Part A, find the tension in the core.
No.
Okay, so let's just start with the forces in the x direction, all right? That's going to give us the x component of tension plus the friction force equals 0. Why did I label this as an equilibrium system?
It's not moving.
Right, constant velocity. You notice those words in the problem, constant velocity? That always means your sum of forces is 0. The only time that sum of forces is not 0 is when you have an acceleration. Object can be moving. If it's moving at a constant velocity, there is no acceleration. So we'll pick it up here on Friday. No. It's just chapters 4 and 5. And remember, like, there was only one problem I put on there to solve, like chapter 5, and that has to do with bank and unbanked. Because I think it covers pretty much everything that chapter talks about. The others are going to be projectile motion for chapter 4. And of course, you have your first 5, which are like, they're like quiz questions.